My name is Jan Belis. I'm from Ghent University, and I have the honor to be the chairman of this first session here, and also of introducing our first speaker of today, Isabell Ayvaz from Darmstadt. You're working at the Glass Competence Center over there, which is quite famous already in the meantime. I'm just having a look at the title of your speech. It is a structural performance of linearly laminated metal fittings for frameless glass shell structures. It's quite a long title, but I'm sure it will be a very interesting talk, so we are looking forward to it. The floor is yours, Isabell.
Yeah, thank you, and thank you that you've joined us on this stage for the first presentation. And for me, it's a pleasure to kick things off with a topic that, in my opinion, combines elegance, aesthetics, with structural ambition and also material efficiency. So it's all about, as it says, transparent shells. And what probably most people will think of if they hear the term transparent shell, they will think of something like that, this shopping mall here in Frankfurt in Germany. So what typically glass shells consist of are two key elements. It's a load-bearing substructure, which takes most of the loads, and the glass itself is only used as an infill to provide insight and light. But that way we lose out on a very huge potential on glass, and I think everyone as a glass enthusiast will know that glass can be quite robust, and we lose on actually using the whole capacity structurally of glass. So what we wanted to try, and we're very motivated to investigate, is how to activate the glass elements in a shell while still not compromising on other aspects like elegance, appealing appearance, and performance in general. How to do so? We actually were aiming to develop a laminated metal connection, and for us it's always referred to as the fitting. When I talk about us, it's actually us at the Glass Competence Center at TU Darmstadt, but also with some great industry partners who were interested or do a lot of shells on their own already, and it was all funded by the German government. Of course, we're not the first to come up with that concept, but there are many others who already thought of how to transfer load between glass elements by laminating something into it. So one of them was, for example, Stefan Marinic. Already back in 2015, he proposed a linear fitting, which he riveted, and he integrated the linear metal fitting into the both interlayers of triple laminate. And from the other perspective, or on the other hand, Timo Feldhut and his colleagues proposed a local solution, and he used milled, dovetailed elements locally laminated into the glass in order to provide a meeting spot at glasstec like 3-4 years ago. And we actually took inspiration from both approaches, so we still wanted to take the linear clarity of the concept of Marinic, but also have that simplified possibility of installation through the local connectors. And yeah, here's an impression of a mock-up we built half through our project, so it actually shows that I would say it's visually appealing, but also due to our local connections, we had simplified positioning throughout the lamination process, but also during the installation process. Now I want to quickly lead you through our development process, which led to the final design. So basic concept, we have the two laminates and a T-shaped bar laminated into the interlayer. But we also wanted to use the edge and activate the structural capacity to transfer loads through that edge adhesion with PVB. And it may seem like a simple concept, but actually we had quite some challenges. And one of them was, for example, geometric constraints. So architects often want to have a clean, clear, slender look. And even if we thought of, okay, we want to be able to implement it in several shell geometries, having different angles in the shell to have a uniform visible joint width. Moreover, of course, we needed to understand what structurally was the performance of the fitting, which loads can it take, but also what if something happens and we need alternative load paths, and how does failure occur. Of course, we thought in 2025 or 2022 when the project started, it wouldn't have added value if we don't think of the thermal performance as well. So that was also an aspect, not the focus of my presentation, but also something we incorporated in the investigation. I would say maybe the most challenging part for us, or particularly demanding, was the manufacturing process of the fitting itself, but also the lamination process, because you had to position it throughout the process, and you also had to gluing it at an edge, which is very small but very long since it's linear. You had to make sure that this will be possible. And I think it was quite interesting. We looked at different methods, and in the end we came up with hand laser welding. And to be honest, I wouldn't have imagined it, because it's a very, very tiny weld, but it's really robust. So here you can see from a test sample, that was a test sample that took 5 tons of load throughout a tensile test. Last but not least, also something we had to think of quite from the beginning, because we have a shell now deleting the substructure, which typically transfers the loads. So installation and the tolerances were also key early on in the process. And for all the elements, we actually had what we used were several tools. So we used a parametric model to enable us to have a digital workflow from early form finding through to fabrication, also directly linked to structural calculations. We needed tests to understand the material properties and the failure modes. And in order to be able to understand where the challenges lie when you really want to build it, we also build a mock-up. Yeah, and as I don't have too much time, I will now actually focus on structural performance. So early on, we asked ourselves, what does our geometry has to look like, or how are the dimensions to be able to take lots of loads? And we performed studies on that, first having simplified calculations analytically, and we looked at different parameters, specifically different stiffness parameters. One of them was the rotational stiffness, and we looked at the effect of flange or web thickness, glass thickness, or thickness of the interlayers. And what was interesting, so for example, for rotational stiffness, as you can see, there are some geometry factors like the flange thickness, which have quite a huge impact. So something we could play around with, and others, like web thickness, not so interesting. We have that part, but we also needed, for having shell structures and designing shell structures, had to also think of simplifying things in a global model. So what we did, as we had that local fixation points, we represented them with spring elements, having always 4 spring elements, representing axial stiffness, 2 shear stiffnesses, parallel and orthogonal to the edge, and also the rotational stiffness. And again, since we also wanted to have it parametrically, we had a link between our parametric model and the calculation software. And this also brings me already to the next step, because of course you will ask, okay, what parameters to put into the model? So this brings me to testing. So here as an example is the testing of our rotational stiffness through a 4-point bend test. So we actually had some specimens and performed the tests. And what we found is quite interesting. So as you may expect, I don't know if I have a laser, but we do have several regions. We have a linear elastic material behavior region, which is typically the one we're interested in the design. When we go a step further, we interestingly see some plastification of our I say the local things called bracket. So we actually have a plastification of this area and nothing happens in the laminate or the glass, which is quite nice because it's a ductile behavior. So if something would happen, we would actually be aware of it because we see that it happens. Yeah, in the end we have failure, and we have failure at different levels. And what we found afterwards, interestingly, was that unfortunately one of those really robust laser welded seams broke. And we wanted to understand that better, and I have one bracket or one fitting with me. So in order to understand what really happened or what was the cause, was by polishing the cross section. And what we found was that the manufacturer we work with, they performed an okay job, but still they just had very tiny welds. So in order to make sure that for us, even if we stay in the linear elastic regime with the design for unexpected loads, we wanted to be sure that if we want to build something afterwards, we have some safety. So we asked them to actually really increase those laser welds. And in the end, actually, for us, for the mock-up, that worked. So here you can see some impressions. We had, since it was halfway through the project, we had special focus on structural performance, but we already also thought of a mock-up which shows or suggests how the connection could look like for further thermal tests. And this actually brings me to the end of my presentation, where I wanted to share for us the most important learnings, but also what our next steps are or what we're doing at the moment. So our biggest learning was that do not do such a project without an experienced partner in metal processing. As we didn't have one in our team, it was quite challenging to find someone who really did what we wanted him to do. And maybe what you saw from the test results, there are some, like, not always it gives the same results. So to control the laser welding process has still huge research potential. What we're doing at the moment at TU Darmstadt is actually prepare some thermal performance tests in order to understand the thermal properties and weak spots of the connection. What still needs to be done, in my opinion, are post-fracture performance and long-term tests. I think this is always, when it comes to research and money goes out, something we aim at but haven't been able to perform yet. And also, due to that welding process and the manufacturing partners, things we need to do is still think about what surface roughnesses and we need, and what moisture and, of course, temperature of PVB will do to our overall shell behavior. It was just a little insight for now. If you have more interest, we have a journal paper at the Glass Performance edition of the Glass Structures and Engineering Journal. Anyhow, if there are any other questions, I am happy if you come to me afterwards. So I thank you for your attention. I'm happy, even if we started with only like 10 people in the room, it's nice that some more have joined us. Thank you.